The quantum properties of elements are also based on the periodic table. The quantum properties are based on the number of electrons that a specific element would have. The electrons themselves are based on the atomic number. The atomic number of the element is how many electrons that element has to work with. By moving along on the periodic table, you're changing the number of electrons. Electrons can only exist in whole numbers. Therefore, they are quantized. And the energies associated with those electrons are what quantum chemistry is based on.
The second half of the experiment focuses on the quantum properties of the different elements, particularly the number of electrons. Elements can only have whole numbers of electrons. You can't have an element with 5.5 electrons. Therefore, the energy associated with 4 electrons and the energy associated with 5 electrons are set. You can't have an energy value that's in between those numbers. It's a quantized property. When electrons are subjected to energy, they increase in energy, they absorb energy, and then they release it in the form of a photon. So when an element absorbs energy, it takes it in, the electron goes up to the higher energy level, and when it relaxes back down to the lower energy level, it releases light. It releases light energy. And the amount of that energy exists along the electromagnetic spectrum. Depending on how much energy was absorbed by the electron and how far back down the electron relaxes, the energy that's released in the photon can vary. Typically, it's in the infrared, the visible, the ultraviolet range, but can also be microwave or even X-ray radiation that's released when an electron relaxes. And particularly in this experiment, we're focusing on the visible region. And this is the region of the electromagnetic spectrum that's associated with color. So color and wavelength and energy are all related. So each individual color is a unique wavelength of light that corresponds to that particular color. And since there is a specific wavelength, an actual length, that can be converted from nanometers into meters. And light can then be turned from a wavelength into a frequency. So a frequency is, if you think of a wave, going back to this image right here, you're thinking of a wave, how long it takes for it to go through one cycle. On this end of the spectrum, it's a very small frequency. Or, I'm sorry, a very large frequency. It happens a lot in a given amount of time. The light particle can oscillate up and down many, many, many times. Versus on the other end of the spectrum in radio waves, it happens at a much slower pace. The light oscillates up and down its wavelength over a longer period of time. And that's related to the speed of light. So the frequency is the speed of light divided by the wavelength in meters. That way, since the unit of speed of light is meters per second, when you divide this by a distance, so how many meters the light travels, it gives you how many times per second the light will go up and down in that wave. Finally, to convert it to energy, the energy is related to the frequency. They're directly proportional. You multiply the frequency by Planck's constant right here, and that will give you the energy associated with that photon of light in the unit of joules. So by going through these unit conversions, you can change the color or the frequency and wavelength of light into the energy that's associated with it. And where this comes into play with elements and molecules is, as I mentioned, with the electrons. So electrons typically want to be at the lowest energy level possible. They always want to exert the least amount of energy. So if an outside source adds a lot of energy, the electron will absorb some of that and go up to a higher energy level. After an amount of time, usually near instantaneous, but very, very quickly, the electron will cool back down or relax down to a lower energy level. And the difference between these energy levels, this amount of energy is released as a photon. It's released as light. So it can either be light that you can see, like the visible region, or it can be light radiation that humans can't really see, like infrared radiation or ultraviolet radiation. And depending on what state the electron is when it starts and what it relaxes back to, these are quantized energy levels. So if an electron is at an energy level of, let's say, 4, it can relax down to an energy of 3 for one set amount of energy, an energy of level of 2, or an energy level of 1. So if an electron is at the 4th energy level, it can only have 3 specific energies that it can release. No more, no less. Only these 3 values, and that's it. That's why these energies are quantized and related to the different wavelengths of light that are released.
Electron configurations are a way to show the unique pattern of energy that the electrons in an individual element would have. These electron configurations are based on the position in the periodic table. The first number in an electron configuration is the energy level of the outermost electrons. This energy level is based on which period the element happens to fall in. The farther down the periodic table, the higher the energy that those electrons have. The middle component of an electron configuration is the subshell, and this also is based on the periodic table. Pre-transition elements, both the alkali metals and the alkali earth metals, have an S subshell. They are only able to hold 2 electrons in the S subshell. The main block of elements, the post-transition elements, have a P subshell. The elements in the main block, or the post-transition elements, are able to hold 6 total electrons. The transition metals are in the D subshell. The D subshell is able to hold 10 total electrons. And finally, the rare earth elements here are in the F subshell, each able to hold 14 electrons. So where an element is on the periodic table describes the individual electron, the last electron associated with this particular element. All of the preceding electrons also have unique individual energies associated with them, and the electron configuration can pinpoint what that unique energy is and base that on its position in the periodic table.
Each electron in an atom has its own specific energy and its own set of quantum values that describes that particular energy. So there are things like the different energy level, the different orbital or subshell, and the different orbital within the subshell, and then what's referred to as the spin within the orbital itself. So as you're going through, each one of the electrons in an atom has all four of these numbers. And an electron configuration is a way to write out all of these numbers and describe what the energy is for that particular electron, and then for an element, what the energy is for all of the electrons within that element. So when you're writing out electron configurations, the number out front is the energy level, and that's based on what, in fact, all of this can be based on where the element is in the periodic table. So in the case of hydrogen, it is in the first energy level, which is just based on the period in the periodic table. The first row has an energy level of 1, the second row energy of 2, 3, 4, and so on. The pre-transition metals have their electrons in the s subshell, and each one of the s orbital, or each one of the s subshells, can hold 2 electrons. There is 1 orbital within the s subshell. The post-transition elements, the electrons associated with those, or the outermost electrons associated with those, are in the p subshell. Each p subshell has 3 orbitals which can hold 2 electrons. So the p subshell can hold a total of 6, and the transition metals, the d subshell, can hold a total of 10 electrons. There are 5 different orbitals within the d subshell, each holding 2 electrons, and for a total of 10. So when you write the electron configuration itself, you're starting with the lowest energy electron, which in every case will be hydrogen. Hydrogen, that 1 electron at the very, very base of the atom, closest to the nucleus, all the way in there, lowest amount of energy, is at the energy level of 1. It's at the lowest energy subshell, which is the s subshell, and there is 1 electron within this s subshell. So that's how you go through and write all of the electrons out within an element. What energy level, what subshell, and how many electrons are in that subshell. In the case of helium, that's the next one. There are 2 total electrons. So it's in the first energy level still. The s subshell can hold a total of 2 electrons, so there's room for 1 more. So helium would be 1s2. When you keep going further in writing an electron configuration, once you fill up one of these subshells, it's full. It can't hold any more electrons. So if there are additional electrons, they need to be put in to the next higher energy level or the next higher energy space. So in the case of oxygen, there are 8 total electrons. The first 2 can be taken care of in the first S subshell. It can hold 2 electrons. After that, there are 6 total electrons left. So going back to this, you've filled up the 1s subshell. So what's next? Oh, you're going to the next energy level. So the second energy level, and starting again with the S subshell. Energy level of 2 in the S subshell, and you can put 2 more of them there. Now you've used or accounted for 4 of the total electrons, so you still have 4 more to go. Looking at the periodic table, moving right along, after in the second energy level, after the S subshell comes the P subshell, and that can hold a total of 6. You had 4 additional electrons left, so these can all fit within the P subshell. And then you have the full electron configuration for oxygen. The first 2 electrons go in the first energy level s orbital, lowest energy. The next highest energy area would be the second energy level, the s subshell, but that gets filled up as well. And then the second energy level in the p subshell, and that can fit a total of 6, and you only have 4 remaining. So all of those can fit into the 2p subshell, and then the electron configuration is finished. Now, as you get to larger elements, particularly the D block, the transition metals, there are 2 weird quirks that are associated with the D block electrons in the transition metals. The first is that even though the periodic table looks like this, where you're starting off with 3s, you move along to 3p, so it jumps down to the next highest, or jumps up to the next highest energy level, 4s, the D electrons are at a lower energy level. Even though this is how it's lined up on the periodic table, these transition metals have a lower energy level than these 4s electrons. While these 4s electrons have a higher total energy, it's easier for different electrons to fill in this subshell and fill in the s subshell first before they start filling in the D subshell. So when you're starting with the transition metals, so in the case of titanium right here, you go through, you filled up the 2p subshell, you filled up the 2s subshell, the 3p subshell, the 4s subshell, and it goes down to 3d. And in the case of titanium, there are 2 electrons that could go in there. 4s is actually more energy overall, but 3d is a little bit more difficult for the electrons to get into. So the 4s electron is filled first, and then the 3d subshell. The next quirk or strange thing, or at least difficulty, with the transition metals and writing electron configurations comes in groups 6 and 11. So these are elements like chromium and that column, and copper and that column. So where this comes into play is, let's say in the case of chromium, This would be the electron configuration of chromium, ending with 4s2, 3d4. The D subshell can hold a total of 10 electrons, and it's very close to being completely half filled. And that is a much more stable arrangement to have the subshell either completely filled or completely half filled. And because the 4s electrons are technically a higher energy than these 3d electrons, one of these electrons can fall back down into the 3d space. So that means that this is now the lowest energy level. The 4s electrons had a little bit higher energy, and the 3D was really, really close to being perfectly stable at half filled. So one of those high energy electrons can fill back in. And so now the full electron configuration for the element chromium would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d5, making sure that that D subshell is completely half full. The same would be true with copper, except instead of starting off with, in theory, a 4, it would be a 9, very, very close to being completely filled. And so one of these high energy electrons could drop back down and fill in that gap. So when looking at electron configurations of the d orbitals, you have to keep these two things in mind, that when you're starting on the transition metal electrons, the energy level drops for the d subshell. And in group 6 and 11, there is this little quirk where one of the higher energy electrons would fill in the remaining part of the D subshell. The last thing about electron configurations is what happens when you have an ion. So in the case of sodium, you have a full electron configuration like this. This is the electron configuration of the sodium element. But many times, especially in chemistry labs, you're not dealing with sodium element, which will explode in water. You're dealing with sodium ions, like those that are in table salt. And an ion is an element with a differing number of electrons. In the case of sodium, there is one less electrons. So, which electron gets taken off? And the electron that gets taken off is the one with the highest amount of energy. So in the case of sodium, the element, there is one 3s electron. This is the highest energy electron that it has. So when the sodium metal reacts and becomes sodium ion and loses an electron, it's going to lose this electron of its highest energy level. Now it's completely stable, and you'll notice when something is, when an ion in particular is very, very stable, all of the subshells are completely filled in. Each of the S subshells has 2 electrons, and this P subshell has 6 electrons. They're completely filled. So this can be seen very specifically in copper and the copper metal ion. So what would be expected would be having 29 electrons and with 3d9 and 4s2, but because of the quirk, copper metal actually has 4s1 3d10. And when you have the ion, you would expect these two 4s electrons, because you would expect 2 electrons to leave this d orbital or this d subshell, but 4s is a higher energy. So what happens is there's copper ion is 2+. It loses 2 electrons. So the 4s electron is the highest energy. That one gets booted off. It gets lost. And the next highest energy level would be in the 3d. So this 3d10 becomes 3d9 for the copper ion. And this can work as well if you have negative anions of the nonmetals. They would behave just like adding in another electron. So going into the next spot within the electron configuration. So this experiment kind of focuses on interactions of color and energy and light, and where the electrons are in terms of their energies and what these energies actually look like and how they're described in the different electron configurations. The experiment itself focuses on two different aspects of light and energy. And you're going through, and in the first part looking at a simulation, and the second part is watching videos of the flame test to get a sense of the different colors related to energy and the different elements related to different colors. The simulation itself is just relating to the wavelength of light to an individual color. This can also give you RGB values, hexadecimal codes for exactly what these colors are. And you can vary the color either through the slide bar or typing in a specific color. You're going to go through and write down the color for the indicated wavelengths, and there are also a few colors in the report itself that you can go through and match approximately what the wavelength is for those individual colors. As mentioned previously, the different colors or different energies of light relate to how they interact with different molecules and different chemicals. When you look at or think about the electromagnetic spectrum of all the different wavelengths of light, the different groups with different energy levels are associated with different energy transitions of the element or the molecule. While some higher energy wavelengths focus on electronic transitions, lower energy wavelengths focus on other transitions, such as bond frequency, or how the two atoms hooked together through a bond vibrate between themselves, or microwaves, which can look at how a molecule rotates. So this first example, or this first simulation, you're looking at these different colors, these different wavelengths, and relating the color that you see with whatever the wavelength is. So you get a general sense of the visible region of the spectrum, the visible region of the electromagnetic spectrum, and what types of colors are associated with either high energy or low energy, high frequency or low frequency, high wavelength or low wavelength.
The flame test is a qualitative experiment used to identify different elements. These elements all have different and unique energies associated with them based on the energy of the different valence electrons, or the electrons in the most active energy level, those outside electrons. And by summing the different energies of all of those electrons, the different elements give unique colors. Something like sodium gives a bright orange flash, very typical of when you're burning wood or something else. Other elements can give other intense colors, such as lithium with a bright red flame, or copper with an orange, with a bluish green or almost teal flame color. These individual flame colors are specific and unique to the different elements. If you were to look and separate the individual colors, you would be able to see a pattern associated with the different elements that is based on the energies of its electrons and resulting in the color that you can see in the flame test.
The second portion of the quantum part of the experiment is looking at that video on YouTube. And this is a video of the flame test. And in the video, they're burning a lot of different elements in a high intensity flame. So these elements are solutions of chemical compounds. So please note that these are ions and not the actual element themselves. So the flame test is a way to qualitatively identify what metal ions are present in a sample. So when these solutions are burned, they're subject to a lot of high energy. And this energy is absorbed by the electrons in the metal ions. And as those electrons relax, they release photons of light. They release those specific amounts of light, which all combined together produce unique and specific colors. So each one of these different elements will produce a different colored flame when they're burned. If you were to take these individual colors and separate them into each individual component, you would see the multiple different unique and specific color pattern that's used to identify actual metals in different samples.